Hello everyone. In this video, I will explain in details page 21 of our Boolean booklet. This page summarizes algebraic properties, postulates, and theorems, which we will use to simplify Boolean expressions. We also use truth table to prove that the Boolean expressions are equal. I would like to begin by going over postulates and theorems. Postulates are self-evident truth, so the statement proven themselves. I would like everyone to note that these are representing the symbol that you put it through AND gates. Alright, and this one is the inverter. This one is the OR gate. And also this one and an inverter as well. Okay, so in AND gate, as we mentioned in previous lesson, if you have 0 and 0, it has to be equal to 0. 1 and 1 equals to 1. 1 and 0 equal to 0. And for the inverter, you invert the signal of 1, then it turns into a 0. For OR gate, you can see that as soon as you have a 1, your signal will be 1. The only time that you have a 0 when both of your inputs are equal to 0. Before I prove some theorem for you, I would like to remind everyone of some terminologies. So if I have a bar on top of A, I can say that A inverted or the inverse of A, or I will say complement of A. Okay, or I can say not A. Alright. If I have the double bar on top of A, I will say double complement of A. Alright, so let's keep this in mind. So let's prove some theorem. Again, for this particular operation, think of it as AND gate. Okay, this one is the inverter. Think of this as OR gate. And this one is also the inverter. Okay, so let's prove a few theorems. So in an AND gate, if I have A and 0, the output has to be 0. I have to have a 1 in order to consider if I have a 1 as the output or not in an AND gate. You can only have the output as 1 when both of your inputs are equal to 1 in an AND gate. Alright, so for A times 1, think of it as algebra. If you have A times 1, you have itself again. Boolean algebra representing this as an AND gate. So the signal for A goes into this gate. You don't know whether or not A is 0 or 1. So if A is 0, then your output is 0. If A is 1 times 1, then your output is 1. So therefore, in this case, is equal to A. So for A times A, there's no such thing as A squared in Boolean or in digital gate. A and A in this case is just equal to A. Alright? So I would like to prove this one. I would like to prove this for everyone. Okay? So let's prove it here. Before I start to prove, I would like to remind everyone that providing proof to prove, we need to convey every single step. You want to convince the readers that I want to prove this equal to that. So I don't think it's a good idea to skip any step or not writing some important details in this case. Okay, so you will see that I will try to write every single step to make sure that I include all the details that I am using to prove my statement. So let's prove A and A bar is equal to 0. So if I let A equal to 0, then complement of A is equal to 1. So let's put it into the statement. So 0 and 1 has to be equal to 0. Okay, so you see that now it's equal to my A. Right. So if I let A equal to 1, then complement of A is equal to 0. So then I have 1 and 0 will be equal to 0 as well. So you see that these two are equal to each other now that I prove that my statement has to be equal to 0 on both. Alright, okay. What about the inverter? So I have A, I put it through an inverter, I put it through another inverter. So if I have, you let A equal to, okay, let A equal to 0. Out from this inverter, you had 1. You put another inverter, you switch it back to 0. You see that this and that equal to each other again. Okay, so if you let A equal to 1, out of this inverter you have 0. You put another inverter, you turn it back into 1. Therefore, you are proving that double complement of A is back to its original signal. Alright, so let's move on and prove our OR gate in this case. Okay, remember that in OR gate, as soon as you see an input of 1, your output has to be 1. So the only time that you have a 0 output is when both of your inputs are equal to 0. Okay, so keep that in mind. So think of this in terms of algebra. So if I have A plus 0, it has to be equal to A. Okay, but this one, A plus 1, this time I have it equal to 1 because in an OR gate, as soon as I have the 1 input, my output is equal to 1. Now what about A plus A? What do I have in this case? Alright, so I would say A or A is equal to A. Because, so let's prove it down here. A or A equal to A. So if you let A equal to 0, so you have 0 plus 0 has to be equal to 0, and it's true for the OR gate. If you let A equal to 1, right? So then, in this case, what you have is you have 1 or 1, then it's also equal to 1. Both of your signals are 1, so your output has to be 1. Okay, so in this case, we have an OR. Alright, okay. So the one I want to prove for everyone is this. Okay, so let's prove it down here. A or with the invert of A is equal to 1. So let's prove that. Again, details. So if A equal to 0, then complement of A is equal to 1. So I will have 0 or 1. It has to be equal to 1. Alright, so if A equal to 1, then complement of A is equal to 0. Therefore, I will put 1 or 0 is equal to 1 again. Alright, so they are proven in this case. So, again, it's very simple to say that A equal to double complement of A. Because if you set A to be 0 and then you invert that signal twice, you get back to 0 again. Alright, so keep that in mind. Let's move on to work with some algebraic properties. Okay, I'm going to circle the first two on this side and the first two on this side. So again, this is an AND gate. Okay, this is the OR gate. Okay, so these are called commutative rule. So they are explain themselves. They explain themselves in this case. What I would like to prove to everyone is this one right here. Okay, the distributive rule. Alright, so take a look at this distributive rule on this side of the equation. What we have is we have A times B, A times C. So then it's easy to recognize that I have AB plus AC. Think of it in terms of mathematics, then I should recognize this very easily. However, this particular distributive rule is hard to recognize it. So I really want to prove it using algebra, and I will also use truth table to prove this as well. Alright, so when I prove this, I will write my right hand side down. Okay, A plus B multiplied by A plus C. Okay, I would like to distribute them. Okay, distribute the two brackets. So I will multiply the first element in my first bracket with both of the terms inside the second bracket. Okay, I repeat the same thing for B. So let's see what I have in this case. And I would like to write it in terms of Boolean algebra. Okay, so and I will mix between Boolean and algebra so that it's easy for us to recognize what operation that we should use. Okay, so let's start with A times A. Okay, so I put A dot A plus A dot C plus B dot A plus B dot C. Alright, okay. So I would like everyone to take a look at page 21. And on that page, you found that A dot A is just equal to A. Right? So I'm going to write it like this. Okay. So nothing wrong with writing it like this. The reason I take the dot away because I want everyone to recognize that I have the common factor of A. So as soon as you see a common factor, you should factor it out. Okay, so I have A, then 1 plus C left inside the bracket. Okay, this two term, you rewrite it the exact same. So now, think of this as Boolean algebra. This one you have an OR gate. Okay, an OR gate. So in an OR gate, as soon as you have an input of 1, your output has to be equal to 1. So in this case, I will have 1. So I will write it A times 1, or A dot 1. Okay. So I would like everyone to check on page 21. You can see that A dot 1 is equal to A. Okay, so let me remind everyone of that. A dot 1 is equal to A. So let's go to our page 21. A dot 1 is equal to A. Alright, okay. So I will rewrite my A in this case plus BA plus BC. Okay, so what I have is recognizing this the same again. So I will factor that out. Okay, 1 plus B plus BC. Now notice, okay, I have another OR gate. Okay, the OR gate I have a 1 as the input. My output has to be 1. So in this case, I will have A dot 1 plus BC. A dot 1 is just A, so I write A plus BC. Alright, so what do I have on the right hand side originally? I have this, okay, A plus B times A plus C. In the end, I actually prove that the two Boolean expressions are equal to each other. Alright, so let's take a look at that. I need to prove A plus B times C equal to A plus B times A plus C, and is actually proven. Okay? Okay, again, we need to be reminded that in providing proof to prove, we need to convey every single step. Therefore, it is not a good idea to skip any step or any important details in this case. So let's make a check mark beside all of this, just to remind everyone that it is important to provide details, step in proof. Okay, if you ask to prove something, you need to provide details. Alright, so let's move on to the next page. So what I'm asking everyone to take a look at this is I'm going to prove this again, but this time I will use truth table. Alright, so using truth table, there's certain steps that we have to follow, and I would like to ask everyone to analyze a few things in this case. Okay, to analyze this, what we need to do is I am going to include the details, but I cannot repeat the same columns twice in my truth table. You cannot repeat the columns for conveniences. Okay, so I will demonstrate it, the step, and hopefully in the process you realize that I don't have extra column, and I also don't skip any column. So first of all, you have A, you have B, you have C. Alright, A, B, C. It means that you have 3 inputs. Okay, we have 3 inputs, and we have 2 possibilities of 0 and 1. That means I will take 2 to the exponent 3. I have 8. Okay, 8 combinations of 0 and 1. Okay, so keep that in mind as a reminder to everyone. Alright, okay, so now I have to organize all my column. In here I have input A, input B, input C. And then I should have a column for B, C. Then I should have a column for A plus B. And I should have a column for A plus C. And then I should have the column that I should have A plus B and A plus C. And at the end, I need to prove that it's equal to A plus B, C. Alright, so now you see that in analyzing the detail of your statement, you will find out that you have to use 1, 2, 3, 4, 5, 6, 7, 8, 8 columns in this case. Alright, so let's write it down in our truth table. I should have A, I should have B, I should have C. The next one I should have BC. The next one I should have A plus B. Then I should have A plus C. Then I should have A plus BC. And the last column, I should have A plus B, A plus C. Alright? Okay. Let's write BC here. Okay. So the combination of 0, and 1. As we mentioned in previous class, we should start with the 4 zeros for A, and then the 4 1, 2 zeros for B, then 2 1s, 0 0 1 1, and alternation of 0 and 1 in this case. Alright? Okay, so BC, I should have 0, 0, 0, 0, 0, 0, 0, 1. Okay, so B times C, in this case, I believe this one should be 1. Okay, so I take a look at this two column. I should have 0, 0, 0, 1, 0, 0, 0, 1. So now A plus B, I should have 0, 0, and the rest of them should be 1. Okay, A plus C, I should have 0 here, 1 here, 0, and the rest of them should be 1. Okay, now A plus BC, it means that I take a look at this column and this column. Okay, so I should make sure that I trace the correct columns. A plus BC. So with A plus BC, I should have 0, 0, 0, and the rest of them should be 1. Okay, so now I should write these two columns and I add them together. So I should have 0. As soon as the 0 is a 0, as soon as the 0 is a 0, the only time I have a 1 is when both of them are equal to 1. So now you see that all your combination of 0 and 1 are exact same. So in this case, this is equal to that. So you can see that they are equal and it's proven. Alright.